I'm Depraetere, and today I will present the beginning of our research project, calibrating a ductile damage model for two pipeline steels. Our research is funded by FWO and involves the cooperation of research groups such as Laboratory and Sustainable Materials Science. I will start with a broader overview of the project, after which I will present the approach proposed and more specifically the challenges we are currently facing. Our research project is related to hydrogen gas. Hydrogen is currently seen as essential in the energy transition towards a low-carbon economy. Pipelines have the function of transporting and storing energy, which can be in the form of hydrogen gas. In 2017, over 4,500 kilometers of hydrogen pipeline were present throughout the world. It is expected that this number grows a lot in the coming years due to the pressure of reaching the global warming targets. However, there is a well-known problem when hydrogen comes into contact with steel. Hydrogen degrades the mechanical properties of pipeline steel significantly, which is often called hydrogen embrittlement. This figure illustrates in red the reduced fracture toughness of a certain pipeline steel due to hydrogen gas. This is why it's highly relevant to investigate the effect of hydrogen on pipeline steel. Our research focuses on developing a micromechanics-based finite element damage model that includes hydrogen-assisted degradation. We have two materials available, a vintage X56 pipeline steel and a relatively more modern X70 pipeline steel. The two steels are expected to behave differently due to the difference in production process. Our approach can be divided into three steps, the first step being calibrating a hydrogen-free ductile damage model. The second step is adapting the model to include the physics of hydrogen transport and capture the accelerated failure. The third step is to validate the calibrated models with fracture toughness tests. This project was recently initiated and I will discuss only the first step here, how we are going to calibrate the damage model which doesn't include hydrogen. First, our two materials were characterized. Tensile tests were performed in the longitudinal direction, showing that the X56 steel has a larger ductility and a larger strain hardening than the X70 steel. Sharpie toughness tests indicated that the X70 was significantly tougher than the X56 pipeline steel. A microstructural characterization shows a heterogeneous microstructure typical for rolled steels. Experimental data is required to calibrate the damage model. We performed tensile tests using double notch round bars, with the radius of both notches being equal. The result of using double notch specimens is that upon loading, both notches will deform almost equally. But when the maximum load has reached, the weakest notch of the two will start necking and go to fracture, while the other notch unloads elastically. The advantage here is that we can investigate the damage state at maximum load and at failure with only one tensile test. This is in particular interesting for the tensile test on hydrogen charged specimens, since hydrogen damage might already be visible at maximum load. By using notches with different radiuses, different stress triaxialities will be induced inside the specimen. As a preliminary numerical study indicated, a broad range of positive stress triaxialities is covered by these four notch radiuses. We want to use load deformation curves to calibrate the damage model. For this reason, an extensometer was placed around each notch for obtaining the axial elongation. Two regular cameras were perpendicularly positioned for extracting the diameter reduction, in the transverse T and the thickness S direction. The reason that two cameras were installed is that anisotropy might be expected for pipeline steel. Behind each camera, a light was placed to obtain a high contrast picture, such as this one on the right. After the test, the images can be post-processed by selecting a region of interest and thresholding the images using ImageJ and Python scripting. In this way, we have extracted the diameter evolution during the tensile test. The load versus axial displacement curves for both materials and all 4 geometries are given here. A sharper notch causes an increased maximal load, but a decreased elongation as expected. The most important thing to notice is a strange behavior for the sharpest notches in both steels. A more detailed microstructural investigation shows that this load drop is caused by the occurrence of delamination in the segregation layer. A cut in the transversal plane shows how deep the delamination runs and the position of the crack with respect to the segregation layer. Since a ductile damage model cannot describe brittle behavior, the occurrence of a delamination is a considerable challenge with respect to calibrating the damage model. By analyzing the pictures and correlating them with the force versus diameter contraction in both the transverse and thickness direction can be evaluated. Interesting here is the difference between the T direction, the dotted line, and the S direction, the full line. For the X56 steel, there is little difference between the two. For the X70 steel, a large difference can be observed. This indicates the presence of plastic anisotropy in the X70 steel. The figure on the right explicitly shows the diameter contraction for both steels in both directions, clearly showing a difference between the isotropic X56 and the anisotropic X70. The presence of anisotropy is another important challenge in calibrating the damage model. For the ductile damage model, we will make use of the complete Gerson model, defined by the yield criteria of Gerson, Vergaert and Needleman, complemented by the void coalescence criterion of Thomason. The model has some parameters that need to be calibrated based on microscopical examination and the matching of the previously shown experimental load deformation curves with numerical simulations. Afterwards, the goal is to validate the model by assessing the void evolution using X-ray CT scans and by performing experimental toughness tests and hereby comparing the crack growth resistance curves with numerical simulations. Two important challenges have already been indicated. How are we going to deal with the observed anisotropy and delaminations? Some ideas for taking these two into account are listed here. I ordered the approaches going from pragmatic, requiring little effort, to more rigorous approaches, requiring more effort to implement. For anisotropy, we could calibrate the model as isotropic, with the average diameter as input. Another option is to evaluate the crack growth direction for the fracture toughness test and calibrate the model using the corresponding orientation. The third alternative is to explicitly model anisotropic plasticity into the damage model, requiring more tensile tests in different directions. Concerning delaminations, we could try to calibrate the model using only specimens that do not show delaminations. Or we could use another specimen geometry, where high triaxiality values are reached in a region further away from the segregation layer. The other option is to explicitly model the occurrence of delamination by locally releasing the symmetry boundary condition. We are currently investigating which of these approaches to follow, keeping in mind the balance between work effort and satisfying results. In conclusion, the effect of hydrogen gas on pipeline steel is of high interest nowadays. By using double notched round bars, we can assess two damage states with only one tensile test. We will perform model calibration by microscopic investigation and tensile test of notch specimens. The delamination and anisotropy that were observed during the tensile test complicate the calibration procedure significantly. In the future, the effect of hydrogen on the material behavior will be evaluated and the damage model will be validated using fracture toughness tests. Thank you for your attention, and I'm open for your questions.